Exactly. Exactly.
Good. Okay, so let's get started. So let's start with a few announcements. So we have a makeup lecture this Friday. If you had seen the schedule, it was posted because we couldn't do the makeup lecture the Friday before the spring break. If you remember, there was a conflict with the candidates Friday. So I had rescheduled that to today, not today, to do this week. So if you have the time, please come. I hope that many of you will come. If you have a conflict, we will record it and put it up, but hopefully many of you who are actually in section 1 can come, so we can have a good lecture. Okay. So that's one announcement. The second one is the lab is due next week. For some reason on the schedule, it says lab 3 is going to be out today. That was obviously a mistake. We don't give out one lab when the previous lab hasn't even been turned in. So I'm going to change that. So you don't have to panic that another lab is going to come out before you even finish this one. So we will hand it out after you turn in your lab 2. Okay, but there will be a homework coming out because it's been a while since I did a homework. Okay, so I'll give out a homework later today. So just keep an eye out for that. Okay, so let's continue from where we left off last time. So just to recap, we talked about leader election, which is the problem of selecting a distinguished node as a coordinator of some sort, of a leader of some sort for any distributed application you are thinking about. And we talked about the problem of how do you implement a distributed lock. Okay? And the second problem is particularly difficult in the presence of failures, because when you have client failures and if the client happens to be holding the lock, then you got to figure out how to recover from this problem, because either you have to change the semantics of the lock or you have to figure out the client failed and do something about it. Okay, so that is where problems get complicated, but there are ways around it, as some of the suggestions that we talked about last time get implemented into the notion of a distributed lock. So we are going to continue from that point on and talk about distributed databases and distributed transactions today. Okay? Just as a way, although this material borrows heavily from the database literature, a lot of it is also interesting in distributed systems, because in many cases you have to implement a set of actions and provide their transactional semantics. Okay? It doesn't have to be actions on a database. It could be any arbitrary action that you may be performing. In fact, the lab that you are currently doing, which involves ordering an item, if the catalog is on one machine and the order server is on another machine, technically you want a transaction so that you can check whether the item is on stock and purchase it. Okay, that involves multiple machines, that involves atomic operations so that you get consistency. Because you could technically check the stock and the stock may be non-zero, but by the time you place the order, someone else may have bought the item and you will basically get an error. Okay, so unless you actually implement transactions which allow you to roll back everything and not have inconsistencies and so on. But however, for lab 2, you are not expected to implement transactional semantics, but something for you to keep in mind that there may be all sorts of race conditions that cause issues. So you at least got to make sure that there are no errors in what you do. Okay? But let's talk about transactions. If you've taken a class in databases, this will be very clear. But for those of you who haven't, let's just take this simple example of a transaction and what it tries to do or why we need it to begin with. Okay, so let's take a simple database. Let's take a bank database that has account information for its customers. Okay, let's just look at the balances that the customer have, and then what we are trying to do is essentially we have 3 clients, okay, A, B, and C, 3 customers, A, B, and C, and customer A is trying to transfer $4 from its account to customer B's account, and customer C is trying to transfer $3 from its account to B's account. So there are 2 transfers that are taking place into account B, okay? One from customer A and one from customer C. Okay? So we could see this set of operations, okay, and so you will see that here you should think of the y-axis as time. So client 1 reads, client 1 in this case is actually a transaction on the database, is reading the account balance for A, and it is deducting $4 from that account. It writes 96 back to the database. Okay? And then we assume that this is a time shared system, so the transaction is just a process in the system. So maybe another transaction gets scheduled as is shown here. Okay? And then that transaction reads the balance for customer C, and it deducts $3 from that account. Okay? And now you got to put that money into B's account. Okay? So you will see that what might happen is, because of scheduling, you might switch back to transaction 1, and then you might now read B's account in order to add $4 to it. And then maybe you get scheduled in the way where transaction 2 runs, it also reads B's account, and both of them have actually gotten $200 as the account balance. And then B is going to add $3. Okay, so the account gets incremented to 203. And then and then transaction 1 goes and adds $4 to that account. Okay, so the account balance becomes 204. So you will see that that's an error, because you are supposed to transfer $7 from 2 accounts. But what happened is, because you read the account balance, okay, and then you basically overwrote one balance with the other, okay, you essentially have an inconsistent state in your system. Is this clear? Okay. This is simply because your operations on the databases are simply getting interleaved in a way that gives you inconsistent end results. Okay. So now how do transactions? Well, think of transactions as a higher level mechanism that gives you atomicity. Atomicity essentially says that when you perform a set of operations, either all of those operations succeed or none of them succeed. You won't have a scenario where some of the operation succeeds and other don't succeed. Okay? At some level, it's almost like a critical section where you've taken a lock on those operations, okay, but you are guaranteed that all of them actually execute or none of them execute. Okay? Even if the process crashes in the middle, any operations that it has performed can actually be undone, which you will not get if you just had a trivial lock implementation. Okay? So that's what transactions are going to give us. So they obviously have their origins in databases, because when you are performing operations on databases, you wouldn't want that kind of scenario to occur. Okay? So then the question is, how would you actually go about implementing it? Okay, if you think about this from a perspective of a lock, okay, you could have said, let transaction 1 take a lock on the entire database, because it's a shared data structure. Right? So you would essentially do all of those 4 operations at once. Okay, then you release the lock, then transaction 2 takes the lock, and it performs all of those 4 operations, and you get a good result, which is what you should get, which looks like that. Okay, does that make sense? Okay. Now clearly you don't want to do it this way, because if you actually give a global lock to an entire transaction, then nothing else can happen on that entire database, regardless of how much data there is in it. Okay, so you do want transactions to execute concurrently while providing this kind of property, okay, without actually implementing a full global lock, which is also what we would give you that, but you don't really want that, because it will then sequentialize or serialize all of your transaction. Only one transaction will execute at any given time. Okay, and then if you have thousands of transactions in your databases, your throughput will really be abysmal. You don't want that to happen. Okay. So this is where we are going to study how to do better than just doing very simple locking. Okay, but first let's come back to the properties that any transactional system gives you. These are called ACID properties. That's an acronym, okay, which stands for atomicity, consistency, isolation, and durability. Okay, if you've done databases, you will hear about ACID properties that any transactional system gives you. Okay, so what does that mean? Atomicity means all or nothing. Okay, which means that if this transaction is performing these 4 operations, okay, either all of them succeed or none of them succeed. So if the transaction crashes in the middle, okay, the transactional system guarantees that even if it has actually written partial data, that will be undone. So you won't have a scenario where you deducted that $4 from A's account, the transaction crashed, and the money disappeared. That will not happen, because the transaction doesn't finish. You can undo whatever partial operations it has done. That is called atomicity. Okay? That's more than locking, just so that you know, because you can undo things if the operations don't succeed all at once. Okay? Consistency essentially says if you have your database or your distributed system in a consistent state, performing a transaction just moves it from one consistent state to another. You will not get an inconsistent state of the form that I showed you on the previous slide. You will never have this. If you start from a consistent state, you will go to another consistent state. Okay? And that's a property you want to provide. Okay? So you want consistency in your system. Okay? Isolation essentially says, also called serializability. So isolation essentially says that even though multiple transactions may be executing in the system at the same time, it looks as if transactions are executing one at a time. Okay? So when you look at the end result, it looks like that is what must have happened, that they actually went one at a time, even though they are all actually executing in parallel. So you get this notion of isolation, which is each one is executing as if they have a global lock, even though that's not actually what is happening underneath. Okay? So that gives you nice properties, okay, where you can reason about, okay, if that happens, then clearly the end result must be right. Okay, and then durability says once a transaction finishes, okay, and writes all of its output, you cannot undo it. Then it basically becomes durable or it becomes permanent. Okay? While a transaction is executing, you can undo anything it has done. Once it finishes, then the changes are permanent. Then there's no going back. Okay? So that is what ACID essentially means. And any transactional system that you see should give you those properties. Okay? You should have all of those properties guaranteed to you by the system. Any questions on this before we look at distributed transaction? Yes, question.
I'm sorry, I think I missed out on what a consistent state is.
What is a consistent state? Okay, consistent state says, well, that's okay. How do we explain this? So think of a database, right? So assume that all data in it is good. Okay? Now you're performing some operations. So we'll assume that you go to another good state, which means that all of what you've done makes sense. To put another way, if I were to give you a counter example, this would be an inconsistent state where you performed an operation and the end result was not what you expected. So here you are supposed to transfer a total of $7 to B's account, but because you overwrote each other's rights, you essentially ended up with an inconsistent state. So that is basically another. So this should not happen is another way to think about it. Okay, any other questions? Okay, so now let's think about going from, let's talk a little bit about transactions, then we'll think about going to distributed transactions, which is where we are headed. So if you have any transactional system, the way you are going to implement transactions in your code is basically you're just going to use a begin transaction at the beginning of the code, end transaction at the end of the code, and the system needs to ensure that all of the properties I talked about in the previous slide holds for all the instructions that sit between begin and end transactions. Okay, so that's essentially how you encapsulate a set of statements with a transaction. Okay, and I'll give you an example here. So let us assume that you're trying to book a plane ticket. Okay, the plane ticket actually involves multiple segments. Maybe there's no direct flight from point A to point B. So it involves that you go to some other location or maybe more than one stops and then get to your destination. Okay? So to book that, make that reservation successfully, you have to essentially reserve a ticket on each of those segments. Okay? It doesn't help if you have 2 of the 3 segments. You can't still travel. You need either 3 or nothing. Okay? So this is a very simple example of having a transaction encapsulate essentially those 3 bookings. So essentially to make a booking to go from, let's say, New York to New Delhi, you have to essentially go and reserve one segment which takes you to Paris. Okay, and what this is saying is if that segment does not have any tickets, then you just abort the transaction. You can't do it. But if that succeeds, then you go and book the next segment which takes you to Athens. And again, if that segment is booked, then you say abort the transaction, and then you do the 3rd segment. And if all of those 3 succeed, then you're done. But if any of those fail, then you essentially have to undo whatever you've done. Because if the last one fails, remember that these 2 have actually been reserved for you. So you've got to undo them, because there's no point in having partial reservation. Okay? That is what a transaction will allow you to do. When you say abort transaction, it will undo everything that the transaction has done so far. Okay, the system will undo that for you. You don't have to go and undo it in your code. Is this clear? Okay, so essentially you will have things like begin transaction, end transaction, abort transaction. These are all things you will write in your code to implement a transaction in your application. Okay, and then there are reads and writes that are actually going to perform the actual reads and writes to the database. Okay. Now, having talked about transaction, let's talk a little bit about what distributed transactions. Okay, so, in order to think about distributed transaction, you got to distinguish them from what are called nested transactions. Okay, so, let me explain the difference between the two. So, the picture on the left here shows you an example of a nested transaction, and the one on the right shows you what a distributed transaction. Okay. So, in a nested transaction, you essentially have two transactions that are nested in a parent transaction. So, you will have one begin transaction, and in there is a smaller transaction which has its own begin and end, a second transaction or more than one that have their own begin and end transaction, and the whole thing is encapsulated in a larger transaction. Okay. Why would you do something like this? So, maybe you are again making a travel booking and you want to get a hotel reservation and an airline reservation. Okay. And those two databases may be distinct databases. So, to make a booking in each one, you got to essentially have your own transaction on each of those databases, and then you combine them into a bigger one because you want the whole thing to succeed. There's no point in getting a plane ticket if there's no place to stay or vice versa. Okay. That is what a standard database system would do. Okay, that's not distributed at this point, even though there are actually transactions operating on two different databases. Okay. If they are operating on a single database, you probably don't need the sub transaction. You could just have one big transaction that does all of those operations. Okay, because you have two independent ones, you need to have transactions on each of them and then one parent transaction. Okay. So that's what is referred to as a nested transaction, because one transaction nested in another. Okay. Here is an example of a distributed transaction. In this case, your database spans multiple machines. There's one database, okay, but it's a large database. So it doesn't actually sit on one machine, it is split across multiple machines. Okay. So you're still now performing a transaction on this database. It's a distributed database. So that database looks like one logical database to the external system. So you essentially write a transaction, but internally you might actually have to implement them as sub transactions on different parts of the database that reside on different machines. Okay. This is why the transaction itself has gotten distributed across machines. Okay. That's called a distributed transaction. Okay. So you will see that there's some difference between that and the nested case. Okay. Yes, question. Okay, so good question. The question is, could you have a distributed transaction be the one of the nested transactions? So it is possible that each of these databases themselves may be distributed databases. So that transaction you are performing on the database itself is a distributed transaction. So in other words, you can also have distributed transaction be nested. That's really the question you're asking. That is of course possible.
So say in that scenario, one of the sub-transactions from a distributed transaction fails, does the whole nested thing fail?
So the question is, if in a distributed transaction a sub-transaction fails, would the whole thing fail? If you give asset properties, that has to happen. If any operation inside a transaction fails, whether nested transaction or global, the whole thing has to be undone. Okay, so you have to abort the entire operation. Okay, is this clear? Okay. So now let's talk a little bit about how you can actually go about implementing these things. Okay, how do you provide these properties? So I'll describe two methods. Okay, one is called workspace based and the other is called logging based, okay, which are used to implement transactional system, and you see that some of them are also well suited to distributed transaction. Okay, both of these methods were designed to implement single machine transactional system, single database. Okay, but they actually generalize quite well when you look at distributed transactions. So similar techniques work. So let's talk about each of them. Okay, we'll start with private workspaces. So in this case, what is going to happen is when you start a transaction, okay, the transaction is operating on a database, say. Let's assume that you make a copy of that entire database and give it to the transaction. So it has its own private working copy. Okay? And it's going to perform some operations and make some changes to that working copy. Okay? Because all the changes are being made to a private copy, nothing has actually changed in the real database yet. Okay? All the changes are local and being made to private copy. Okay? And when the transaction commits, you are simply going to copy the changes over to the original database and they become permanent. Okay? But if you abort the transaction, you simply throw the working copy away. There is nothing to undo because you never changed anything in the actual database. Is that clear? What the notion of private workspaces is. So every transaction that's operating on the database is given its own copy. All changes that it makes to the database actually are performed on that private copy. If you are going to commit the transaction, you just copy any changes that were made over to the original database. If not, you just throw it away and then there's nothing to do, nothing to undo really. Okay, so yes.
Similar to what we do in Git, essentially, like cloning the repo and making changes in our local site, and if the changes are accepted, then they are pushed to the main line, otherwise they are just residing in our own local.
Okay. Question is it what you will do when you are doing source code control? When you actually commit changes in source code control, you will get a notion of similar to a transaction, right? So you are pushing changes and committing that, but you are always it's always fine to throw away your changes and nothing is good. But keep in mind that that's just a concept that seems similar to database transactions. It is not exactly the same because our source code control repo may not give you all of the similar asset-like properties. Okay? But having said that, it is a similar concept. Okay? Because this is actually happening on databases or actually distributed applications. Okay, so now this is all fine, but you should realize that if your database is large, you are not actually going to want to make a copy every time a transaction runs. Okay, 1 gigabyte database, are you going to make a copy every time? Doesn't make any sense. Right? So then the question is, how do you make this practical? The idea seems simple, seems easy to understand, but it's not at all practical to do it that way. Okay? So the way this is actually going to work, that is what this picture is about, is you are going to use a specific technique called copy on write. Okay? It's called COW. It's an acronym for copy on write, which is an efficient way to make changes while sharing copies. Okay? It's also referred to as lazy copying in many cases. Okay? A typical copy is what is called eager copy. You actually make a real copy, and now there are 2 copies floating around. Okay? In copy on write, okay, you essentially have a virtual copy that's pointing to the original. Okay? But you haven't really copied the data. You just essentially said this database is the same as that database. So you basically have pointers that are pointing to the same underlying data. Okay? And what copy and write essentially says is when you are actually trying to write or modify a file or a block in that database, that is when you are going to make a copy for only that portion of the database, not everything. Okay? So you are going to lazily make copies only on demand, only when something is diverging from the original copy. If there are no changes, you are going to have no overhead of copying at all. Okay? And that is essentially what is shown in this picture. Your question, yes.
So you only make a real copy if it changes, but otherwise everything else is this lazy copy, which is like a pointer?
Yes, so that's exactly what I'm going to explain. The answer is yes. So here is your database, okay, which is basically, let's say there are 3 blocks in the database or 3 records in the database. So essentially you have to realize that whenever you have any data on disk, you are going to have an index or a metadata that's pointing to the data. Okay? So this blocks labeled 0, 1, 2, that's the actual data. This is essentially an index, a table that says block 0 is stored here, block 1 is stored here, block 2 is stored here. So essentially the index is a set of pointers that point to the actual locations of the blocks on disk. Okay? So that's your original database. So now if you want to make a copy for a workspace, you are simply going to replicate this index, not the actual data. So you will see that now there are 2 indices. Okay? And initially both indices have the same information, so they are pointing to the same blocks. Okay? That's the second index is your private workspace in this case. Okay? That's your copy on write virtual copy. Okay? Well, now let's assume that you start modifying, because that's executing a transaction is going to start modifying some data. Okay? Maybe it writes some new data to the database. Okay? So essentially you have 3' that you have written. Okay? So what you will do is you will actually write 3' and extend the pointer, saying now there's one more record and that points to 3'. Okay? That is not in the original index, it's only in the copy. Okay? Perhaps you also go and modify block 0 that already exists in the original database, or record 0. In this case, you are going to make an actual copy of 0. That is where copy and write comes in. So you make an actual copy and then you modify the copy. So you will see that now the original data block is still pointing to 0, 1, 3, but the copy is pointing to 0'. Okay, so that's when you made a copy. You could have made that copy when you started. That would have been eager copying. This is doing lazy on-demand copy. Okay, that is why it's called copy on write. Okay. It's a classic technique in distributed system. You will see it in many contexts. This is the first time we have encountered it in this course. Okay, but you will see that many file systems, many storage systems, they will essentially use this approach, especially when you have to do efficient large-scale copy. Okay, you will do copy on demand. Okay, is this clear? So this is just copy on write. The transaction still has not committed. So if you decide the transaction has to abort, you're simply going to throw this away and just delete all the new pointers you have actually created. Okay, so essentially in this case you will delete 0' and 3'. Okay, you at least have to track what changes you made in order to throw it out. Okay. But on the other hand, if you want to commit these transactions, these changes have to be now inserted into the actual database. So you are going to essentially modify, okay, this index, and you will see that block 0 now points to the new copy that was written, which was 0'. Okay, and then you insert 3 so that it points to 3 as well. Okay. Now the changes have actually become permanent. Those changes are visible in the original database. Okay, is that clear? So this is called using a private workspace and using copy on write. Okay, and then when you make the changes visible, that's essentially when your transaction is committed. Okay, yes.
Then, like, 2 transactions happen at the same time.
Yes.
Like, keep the data consistent.
Yes. So the question is, can this actually give you consistency? Okay, that's a great question, because just by doing this, there is no guarantee of any consistency. You could have 2 transactions that are operating. Each of them have their private workspaces. Both of them modify block 0. So you have 2 copies of block 0, 0' prime and 0 double prime. Okay, transaction 1 has committed and transaction 2 goes and overrides whatever it wrote. The same case that I showed you where the bank record was getting overwritten might occur here, because we haven't said anything about locking or anything of that sort. Okay? So this is simply saying you can essentially make a copy and throw out changes that you don't need. Okay? But when you commit, you have to be careful. You don't want to have write conflicts. So these are all things we are going to see in just a little bit. Okay? So this is necessary but not sufficient is the way to think about it. Yes, question? Okay, question is, will you have fragmentation and how do you deal with that? So disks, actually, if you use fixed size blocks, okay, don't have fragmentation, because disk is a random access device. Okay? You don't need all the data to be actually stored contiguously on disk. In fact, file systems don't do that. If you have a file stored on disk, the blocks could be scattered everywhere. Because you have a pointer, you just guess, and it's a random access device, you can access data from anywhere on disk. That's not going to cause fragmentation. Fragmentation is caused when you have holes in your storage space where you cannot actually store any useful data. Okay? The data is scattered over disk, that's a given. Okay? But the kind of fragmentation that you learn about in undergrad operating systems, where you have variable sized memory chunks, that won't occur here. Okay? Any other questions? Okay. So that's one method, which is private workspaces. Let's move on to the next one, which is how do you do this differently. And here is a second method, which is called write-ahead logging. Okay? So in this case, when a transaction is executing on the database, you don't make a copy. You actually start making changes to the original copy. Okay? So you say, I want to modify a record, you go modify it in the actual database. Okay? But then if the transaction has to abort, there has to be a way to undo your changes. Okay? If the transaction commits successfully, the changes are already in the database. There's nothing to do. Okay? But if you have to abort, then you already made changes. You have to undo them. So to undo these changes, you have to keep track of what changes a transaction actually makes. These changes are tracked in a separate file called a log. Okay, every read or write operation, specifically write operation, is logged. So you know that this transaction went and made this change to this record, and the record value was X, now it is changed to Y. So you keep track of all of these changes. So if you have to undo it, you look at all the changes that were made by the transaction, and you can undo them because you track them. Okay? That's the basic idea. And essentially, this is called a write-ahead log. Okay, so you are going to keep, for example, in the write-ahead log, your transaction ID, the block number you changed, the original value, and the new value. Okay, so you keep the old data and the new data in the log. Okay, so now you know that if the old data is this and the new data is this, you can just overwrite the new data with the old and undo the changes if you want to. Okay, because they are all stored in a log. Okay. So that's essentially the basic idea. So if you are going to abort, you are going to read the log records and you are going to undo changes. This is called a rollback. Okay, because you actually made changes, you got to roll the changes back. Okay. In private workspaces, there was nothing to undo because you never actually wrote to the real database. You made a copy, so you just threw the copy out. Okay. Here you got to go back in time to where the database was before the transaction began. Okay, and that is you are going to essentially do a rollback operation to achieve that property. Okay. Now, so you essentially read the log backwards and look at every change that was made. I'll show you an example and just go and undo them. Okay. Now, both of these will work for distributed transactions as well. Okay. Workspaces and logs, although they're designed for standard transactional system, work in distributed settings. So it is easy to take them and make a distributed version. Okay, in a distributed transaction, you can think of every copy or every machine is going to have its own private workspace. You are going to use copy and write techniques and so on, and you just undo the transaction if you don't want to. Otherwise, you commit. And the same is true of the log. Okay, so the technique is not specific to whether data resides on one machine or multiple machines, so it generalizes to distributed environments. Okay, we will talk about how to make the commits atomic, because I did say that in both cases you don't want two transactions trampling on one another. Okay, you still want atomicity property. We will come back to that when we talk about fault tolerance and things of that sort. Okay, we are not going to talk about that today. Okay, so here is a very simple example of transaction that is making some operation. So we'll assume the database has only two records, X and Y. Okay, just two values in the database. Both values, let's say, are initialized to 0 as is shown there. Okay, then you actually have a transaction where you perform some operation. You add 1 to X, then you add 2 to Y, then you essentially do Y times Y to X. Okay? And every time you make these changes, you are going to have a log. So you will see that the log says the value of X before the operation was 0. After the operation, it was 1 after you do this operation. Then you execute the second statement, you write another entry to the log saying before value was 0, after was 2, and so on. Okay, and then, so you end up with 3 entries in the log. Okay. At any point, if the transaction is going to abort, you are going to essentially go read the log backwards. Okay. Say, okay, the value is 4, let's replace it with 1. Then you say the value of Y is 2, let's replace it back with 0. And you say value of X is 1, let's go back to 0, and you end up with 0, 0 again. Okay. So the rollback involves reading the log backwards and undoing all the changes. And then you are back to where you began. Okay, yes. Okay, that's a good question. The question is, do you write all these changes in your own log or a common log? In this case, because there's no private workspaces or anything, you have a log for your entire database or the file system or whatever distributed application. It's one log. So each of these operations has to be tagged with a transaction ID, okay, which is what is mentioned here. So you are going to have a transaction ID, so you know which transaction made that change. So when you are undoing those changes, you got to only undo the changes made by that transaction. Okay, so that's how you are going to do it.
If you have two failing transactions and one succeeded transaction, I guess you also have to check what changes to undo, because if the succeeded transaction has overwritten X, for example, you don't want to reverse the changes the succeeded transaction has done.
Right. So the question is, if there is a transaction that has committed and another transaction that has actually failed, if you are undoing the changes, you don't want to undo the changes committed by the succeeding transaction. Okay? So if indeed there's one transaction made changes and another transaction is aborting, okay, you shouldn't have a case, you should not have that case technically, because what you have is a write-write conflict. Okay. If two transactions are changing the same data item at the same time without locks or anything of that sort, you're trampled on each other. So it's better to undo both transactions, not one. Okay. Technically both of them have to be undone. If you committed one, then the other one shouldn't actually undo the first one. But if you just look at the log, you don't know what to do. So you shouldn't actually have that case. If you have a write-write conflict, both transactions should abort. Okay. Or one transaction should see that if you make the change, it will result in a write-write conflict and abort before you even have that scenario. Okay, so that's how you should do it. But yeah, if you have the scenario you mentioned, you will have problems. Yes.
So that means that things are actually happening sequentially, right? There's no actual concurrency.
Okay, question is there a sequential execution or concurrency? We'll see that you should have concurrency. If you did, it should appear as if everything is sequential, although in reality everything is concurrent. Because if you actually do everything sequentially, you don't really need a lock. If you know that there's, there's only one thing executing at the same, but you will not get any good performance. Essentially, throughput will go down if you execute one transaction at a time. Right? So that is a problem. So you will actually want concurrency.
But that would mean that you could come across that problem.
Yes, so you will, if you are actually, we'll talk about concurrency control in just a moment. So of course, there, if you don't do this right, you will get write-write conflict. So either you got to have fine-grained locks that prevent it to begin with. So the short answer to your question is, if you have normal concurrency control, you will not actually have that case, because you are going to essentially have locks. Okay, you will not locks on the entire database. You could have locks per data item. So one transaction wouldn't actually overwrite anything the other transaction did, because by definition the other transaction holds the lock, so it cannot proceed to begin with. Okay, so you should not even have that case to begin with. Okay, but if you did optimistic, as we will see, you will have that case and you will have to do something about it. Both transactions aborting is typically what happens. Okay? Yes, question?
In this example, when X and Y are first changed, why do you need to log the following operations and Y?
Yeah, so that.
Yeah,
so that's a good question. I mean, you could optimize the log by just saying this is the before value. Technically, you don't need the after value, okay, because that's not really useful. You just need to say that this is what you need to restore it to. You could still do the same thing. Yeah, so yeah, you could have only stored one of those two values.
Is it not the case for more complex examples?
No, I think that it is fine to just store the before value. I don't know why the book actually requires that you store both, but that's what it said. Okay, yes.
Can't the log then also kind of serve as like a snapshotting mechanism? Because it's like essentially writing it like it is a log. It's writing down every single transaction that's happening. So like there was some saved state from earlier that it could replay. Up to the point wouldn't say the database server crashed.
Right. So I think you are asking a different question which we haven't gotten to. When we come to fault tolerance, we will get to that, which is, can you combine this with things like snapshot? So if you have to undo a lot of changes, then what might happen is you are replaying the log. Log replay itself can take a long time because there are lots of things to undo. Okay, periodically you can take a snapshot or a checkpoint of the database, which is a consistent state. So often what might happen is you might essentially say, I actually go to the most recent checkpoint and only undo changes that have happened after that checkpoint or things of that sort. That makes this more efficient. But we'll get to that when we do fault tolerance. At this point, we haven't talked about checkpoints or anything like that. Okay, so we'll come to the question that was just asked, which was, how do you ensure that transactions are going to execute in parallel, not sequentially, and yet give us abstraction as if each of them was executing sequentially one at a time. Okay? That is a problem of what we call serializability. Okay? So we want to allow multiple transactions to execute simultaneously. This is going to give us high throughput. Okay? If you put one big lock on your database, you're not going to get this. Only one transaction will execute, and if there are lots of incoming transactions, your system will be very slow. So you don't want that to happen. You want lots of concurrency in your system. Yet, you don't want any conflicts. You don't want transactions to be overwriting each other's changes. So you want it to look like that transaction executed by itself. There's nothing else happening in the system. Okay? So you want consistency. Okay, and then essentially in this consistency, essentially says even though they are executing in parallel in arbitrary ways, the final result should be as if each transaction ran sequentially in some order. What order, we don't care. Okay. If I give you the beginning state of that database and some end state where lots of transactions are executed in between, okay, you will say that the end state is consistent if you find one order of any order where if you executed them one at a time, you would end up with that end state. Okay. This is called serializability. Okay. So, and we will look at examples of concurrency control and so on. Yeah, but let me just show you some pictures of how transactions are implemented. So, essentially the typical implementation of a transactional system. There is 3 layers here. There is a transaction manager that deals with when there is a transaction, a begin and end transaction. Then essentially beneath that is a scheduler which is actually going to take locks, because in reality if you implement this you will need more fine-grained locking, not locks on the entire database, but locks maybe on each record in the database and so on. Okay, so that's what the scheduler is going to do. It could also do timestamping based concurrency control, which we'll see. And at the bottom, you are actually going to have the actual data manager, which is doing the actual reads and write, whatever the transaction is reading and writing. Okay, so you'll have this layered approach in a transactional system, and that actually generalizes very well to distributed case. So in this case now, rather than having all the data being on one machine, you have them on 3 machines. There's still a single transactional manager where the transaction arrives, then it becomes sub-transaction and it goes out to multiple machines. Each of the scheduler is going to take locks on specific data items that that transaction touches that is stored on those machines, and then the data managers are going to do the reads and write. Okay. So this does not give you any details. It's simply showing you architecturally how you take a database transactional system and then make it a distributed transactional system. Okay. Now what we'll do is to actually look at what happens in all of those boxes at a high level to achieve transactional guarantees. Okay. So before we do that, I will talk about serializability with an example. Okay. So remember what I said was, if you have some concurrent transactions that are executing, okay, and you are asked, here is the end state of the database, is it consistent or not? How do you reason about it? So you look at all the transactions. You can take any interleaving. We'll say, let's say they executed in order ABC or ACB or BCA. If you find one ordering where if you executed them in that order one at a time, you end up with that state, you say that's fine, that's good state. If you can find no ordering in which that state would be arrived at, then you say that this is inconsistent. There is no conceivable way by which you could execute them one at a time and end up with this state. So that's an inconsistent state. Okay. And that is exactly what this picture shows us. So here there are 3 transactions. These are all toy examples. So you will see that transaction 1 initializes x to 0 and then adds 1 to it. Transaction 2 also does that and now adds 2, and transaction 3 adds 3. Okay. And now these transactions are assumed to all execute concurrently. So they will execute in parallel. Okay. You will see that those 6 instructions will get interleaved in some arbitrary order. Okay. And then the question is, which one is legal, which means that you ended up in a consistent state, and which one is not legal. Okay. So to do this, you basically, you can look at these statements and say, what is the end result? Okay. So in this case, you will see that if you execute it this way, the end result is going to be x is equal to 3. Okay. And if I ask you, can you execute these 3 transactions in some order where you end up with x is equal to 3? Can you find such an order? Okay, the order is very simple. In this case, you can either execute the first or the second transaction in any order and then execute the third transaction, you end up with x equal to 3. Because this is a toy example where each transaction is just clearing out x and just setting x to some value. Okay. So you could have executed A, B, C. You will see that if you executed them in that order, the database state is x is equal to 3 for that record. Okay. So that's a valid example. So you say that's acceptable. Okay. Here's another one. This one also gives you x is equal to 3, but you will see that in between when it's executing, you are getting x is equal to 0, x is equal to 0, then you essentially go to 1, you go to 2, or you go to 3 rather, and you end up with 3. But we'll take that as well because the end state is still valid. Okay, so x is equal to. So the interleaving does not matter. What matters is what happened at what was the beginning state, what was the end state. If you can arrive at that end state, you are good. Okay? And here is a third interleaving that we will say is not legal, because here you are essentially going to end up with x is equal to 5 because of this interleaving. You will see that the same statements they are executing in this order into x is equal to 5. There is no conceivable way that those three transactions will ever give you x is equal to 5 if you executed them sequentially. Okay, so we will say that's inconsistent. If you get that interleaving, you are not going to accept it. Okay, you are going to have to abort all the transaction and undo them. Is that clear? Okay, so this is just a simple example that shows you what serializability means. Okay, so these kinds of ordering is allowed. Okay, we will take it. This one is not allowed. Okay, so this is what you want to avoid. Okay, so the basic idea is, can you somehow schedule those operations, because they are interleaved, they are executing in arbitrary order to avoid what are called conflicts. Okay, so there are two kinds of conflicts that can occur. What is called a read-write conflict and a write-write conflict. Okay? So write-write conflict should be clear. Transaction 1 writes something and the transaction 2 is overwritten what. That is that bank example I started off with. Okay? That's something you want to avoid. Read-write conflicts essentially says I read some value, okay, and I am doing something with that value. In the meantime, the value is actually changed by some other transaction, okay, for that record. Okay, because the actual value is not different from what I read, there is a read-write conflict. Okay, so you don't want either of those two things to happen. Okay, on the same operation or the same, not operation, same data item. So we will see two ways to, actually three ways to do this. Okay, the first technique is called optimistic concurrency control. Okay. In optimistic concurrency control, you take a good rosy view of things. You will say conflicts are rare. Okay. Let us not bother with locks. Okay. Let us just do away with locks. Let transactions do whatever they want. Okay. But before they commit, we are going to check if the transaction did something that could cause a conflict. If so, we will essentially abort the transaction. Okay. But if things look good, then you just commit the transaction. Okay. So the checks are happening post facto. You let the transaction do whatever they want, and then you check, was there a read-write conflict or a write-write conflict for all the transactions that were executing, and when this transaction is about to commit. If so, you undo. Otherwise, you are good. Okay. So essentially, this is referred to as optimistic concurrency control, because optimistic because it starts with the assumption that conflicts are rare and you don't really need things like locks to avoid them. Okay. Now, there are many advantages. So this works well with private workspaces, clearly, okay, because you don't have locks in private workspaces. Only when you are copying the changes over are you going to check, is there any problem. Okay. If so, you essentially undo. You say that some blocks that you change have been changed by another transaction since you started, so you just abort. There's nothing to do. Okay. So that's easy to implement. The advantages are it's deadlock free. Okay. Is that clear why it is deadlock free? There cannot be deadlocks in this approach. Why? There are no locks, so how can there be a deadlock? There is no lock. Okay, so that should be clear. Okay, high parallelism, because there is no locks, there is no blocking either. So you will get maximum parallelism. Okay, anything can execute with any other transaction. Okay. Disadvantage of this approach is that you have to, if you abort the transaction, you got to rerun it. So you will waste some cycles because you are undoing work and repeating it. Okay. And furthermore, the probability of a conflict is going to increase as the load increases. This by and large works well because if you have a large database, you will say different transactions are operating on different parts of the database. Okay. I may be trying to make an airline booking to go from New York to maybe San Francisco. Somebody else may be trying to make a different booking, and those two operations have nothing to do with one another. Okay. So let them execute in parallel. They don't conflict. So this is your general assumption, that different transactions are going to operate on different parts of the database, and by and large things will be well. Okay, but occasionally you will have two transactions that are actually looking at the same data items in the database. That is when conflicts are going to arise, okay, and that is when you will have to abort. And the assumption here not the assumption. The observation here is the probability of that happening is going to increase as the load or the concurrency increases. If there are more and more transactions executing all at once, the probability that any two will touch the same data item goes up. Okay? So at high loads, okay, you will have lots of aborted transactions because there will be higher chances that there is a conflict and you abort the transaction. Okay. So in particular, at very high load, you will have lots of things executing, but the good put of your system will be low. Okay. Good put is the number of successful transactions. We are executing a lot of them, but throwing out many of the changes that are being made because they are all aborting. So you will have low good put, but high load. So lots of wasted work. Okay. So that's a problem with optimistic concurrency control, which is why many real relational database systems don't actually use this optimistic view. Okay. They say that that's not a good thing because when the load is high, things may actually go. It's like swapping that you have in virtual memory system where a lot of work but not enough good work happens. Okay. So that's a disadvantage, which is why many systems don't use optimistic concurrency control. Instead, they use what is called pessimistic concurrency control, okay, which is essentially saying there may be conflict, so we should try to avoid it at all costs. And the way you are going to do this is by implementing locks. Okay. So rather than a lock for your entire database, you will have a lock for every record in the database. Okay. So your locking is more fine grained. Okay. In some databases, you actually have locks on each field of a record, not even an entire record, to allow for parallelism. Okay. So you grab whatever lock is needed before you perform that operation. Okay. And you hold that lock through some point in the transaction, which means that any other transaction that's trying to read or write is going to be blocked. So you will hold an exclusive lock on that item, so nothing else can actually do the perform some operation on that data item. Okay. You can get other locks on other data items in the system. Okay. So you still get parallelism, okay, but you are not. You are going to avoid conflicts by implementing locks. That's the basic idea. Okay. So essentially, we are going to see an approach called two-phase locks, and then I'm going to come back to why this might still give you things like deadlocks and so on. Okay. So here's a picture that shows you how two-phase locking or 2PL works. Okay. X-axis is time. The basic rule is as a transaction starts executing, every time it is trying to access a new data item in the database, get a lock. Okay. So the number of locks you hold will keep increasing as you say read some value from record A, then go do something to record B and record C. So you'll keep getting locks as you are about to touch each new item in the database. Okay. That is what is called the growing phase. Okay. And the plan, or not the plan, the rule here is that you don't start releasing locks until you are done accessing all the data items you are about to touch. Okay. So once you release locks, you cannot acquire any more locks. That's the rule. Okay. So the number of locks you hold will grow monotonically, and then it will start shrinking, because once you start releasing locks, you can't acquire any more locks. Okay. That's the general rule. Okay. A simplification of this is what is called strict two-phase locking, where you basically just release them all at the end. Okay. You just release them all at once. So you keep grabbing locks, you complete execution, and when the transaction finishes, you release them all at once. Okay. That's going to be the same approach. That's a stricter approach than saying here I'm done with A, so I'm going to release the lock on A. And then you say I'm now done with accessing record B, I'm going to release the lock on B and C and so on. And then the number of locks you hold will shrink. If you do this, you might get a little more concurrency because you hold locks for a shorter period of time. Okay. So the longer you hold locks, the more you're going to block some other transaction. Okay. Yes, question. Yes, that's a good question. Question is, are you acquiring locks for things you are reading and writing? In this case, you are actually going to acquire a lock on an item regardless of whether you are reading it or writing it. Okay. You are not doing things like read-write locks because you don't want conflicts. Okay. But yes, before you touch anything, whether you are trying to read it or write it, you get a lock on that item.
I was wondering if, so if you're querying the database, you kind of, I don't know, do you need to lock the database if you're potentially like reading, you're selecting value, like certain
Right.
values from the database?
So So the question is, if you are actually writing a query to a database, do you actually need to get a lock? Typically, if you send a SQL query and as a relational database, internally it can actually grab a lock, even though you may not have specified a lock in your SQL query. Okay? Even if it's all reads, you can actually get a lock. If your system, if it's implementing pessimistic concurrency control, can grab a lock. Not every database is actually going to give you transactional semantics. If your SQLite, for example, that has no concept of a lock. Okay, there's no transactional properties that it gives you. But if the system actually gives you transactional properties, either you can explicitly have begin or end transactions that encapsulate your SQL query, or there's an implicit begin and end when you send the query to the system. Okay, then with that you will actually get logs. You won't see this happening, that's all happening internally. Okay, this is all done by the system. The programmer is not doing anything. That's the important thing to keep in mind. Okay, you are not expected to write all this locking code. Yes?
Is there a threshold decided for the time when to stop locking? How many logs, after how many logs you have to do the shrinking phase?
Okay, question is, what is the threshold where you start the shrinking phase? That threshold actually depends on the transaction. So if you think of a query manager or optimizer that's scanning the query, and it says after this statement there is no new data item I'm actually going to access. Everything I'm supposed to access in this transaction has already been accessed at least once until this point. That is the point when you can say no new locks are going to be acquired after this point. And then you say, here's the statement that's the last time I'm going to access A. After this, the rest of the transaction doesn't touch A. Then you release A, and so on and so on. Okay, that's how your query optimizer and things of that sort will actually implement this transaction. You could, of course, do the simple thing where you just keep grabbing locks and not have to do all this analysis. You hold them to the end and you release them all. That's the simplest case. That is called strict 2PL. Okay, that's just a variant of this, because it says release them all at once. The shrinking phase is one step. Okay, yes. Yes, I'll come to deadlocks in just 1 second. But let me finish the other question. Yes. Okay, question is, can you assume that the transaction cannot fail if you all have all of that lock? The transaction may abort for any reason, not just a read-write conflict. Remember in that airline reservation example, we said abort the transaction if there are no seats left on that airplane. Okay? That was not a read-write conflict. That just said there's a application level logic said I don't need to continue, I'll abort. So you can abort for any reason. Okay? Conflicts are one of the reasons to abort, but that's not the only reason. Application level code may say if this condition holds, abort the transaction. If the price is too high, abort the transaction. Whatever it may be. Okay? So there's no reason to believe that once you have grabbed all this log, there will not be an abort. You could still have abort at any point until you commit. Once you commit, you cannot abort. That's the only rule.
Yeah, how about the scenario that you release one log and you override and another transaction overrides this variable immediately before you finish the transaction and then you reverse the transaction?
Yes. So the scenario that is being mentioned, if you release a lock here, but you have not yet committed the transaction, another transaction can overwrite it. Okay, and then when you are trying to commit it, what should happen? So remember that just because you overwritten it doesn't mean that it is committed. Okay? If you actually overwrite it and when this transaction aborts, you will see that there is two transactions that are actually, this transaction is aborted. So you have to undo its changes. There's another transaction that actually overwrote some data. That's also a conflict. So you will have to, if you have a proper transactional manager, abort. Writing is not the same as committing. That's the thing. You have overwritten changes. That is true in the example you gave. But that doesn't mean the second transaction committed. You should treat this as a write-write conflict, even though you have a lock and then abort. This won't occur if you have strict two-phase lock, because in that case you hold the lock to the end, so nothing else will overwrite your data, because you are not going to let any other transaction proceed to begin with. Okay? There are all these subtleties you have to think about. Yes. Can you speak up a little? Okay, is read-write log used in real-life systems? So read-write locks are used frequently, okay? But in this case, you want to use proper locks. Okay? Read-write locks are just a way to have more concurrency. You can have multiple readers reading the object at the same time, but if there's one writer, then it blocks everything else. Okay? That's the example of a read-write log. It's used in many scenarios But in this very specific case, when you're taking a lock, you want to make sure that you're blocking everything else, because you might have a read-write conflict. For us, a reading and writing is a conflict of some sort, so you want to ensure that you get the right. But there are databases where if you're just reading, you might get a read lock as well. Okay? But in normal code where you're writing threaded code, that's a frequently used abstraction. Yes?
So in the scenario that he was talking about, we don't want to be in the scenario where a second transaction that's modifying something that the first transaction modified. You don't want that to commit before that one commits.
Right.
Right. Is that something that's implemented in this two-phase locking by a system, or is that something you just have to watch out for on the application?
Right. The question is, if you have two transactions that make conflicting operations, is that taken care of by just two-phase lock? Ideally, if you have locks, you shouldn't have to do extra work. So two-phase locking is safer in that sense than just locking, because you'll see even there's in addition to conflicts, we'll also have deadlocks in some of these cases. Okay, so but if you actually had that scenario, you would have to implement it outside of this, because locking by itself hasn't guaranteed conflicts are not going to occur. Because if you release a lock, some other transaction comes, grabs the lock and makes changes, and you made changes, you abort, or both of them have to abort because it's a write-write conflict at that. So there are all these subtleties you have to think about. Okay? It's just a concept, but making it practical, giving asset properties is harder than just doing this. Okay? So let's go back to that question that was asked, which is deadlocks are possible in this case. Okay? So you can think of two transactions, okay, that are trying to access two data items, x and y. Okay? Transaction 1 starts accessing x. Okay? So its growing phase, it's going to grab a lock on x. Okay? Because these two transactions are executing concurrently, let's say transaction 2 also starts executing, but it accesses y first. Okay? So it's going to essentially grab a lock on y. Okay? Now when transaction 1 continues its execution, it will want y, but transaction 2 holds a lock on it. And transaction 2 will want a lock on x, and 1 holds that lock, and now you have a classic deadlock, where you hold one lock, you're waiting for another lock. Okay? So that's going to occur in this case also, because this doesn't tell us anything about order in which you access, grab locks or anything like that. If you grab them in arbitrary order, you might get a deadlock every once in a while, and your system will basically not make any progress. Okay? So you got to watch out for these kinds of things. Okay? So there's a simple rule that allows you to avoid deadlocks when you are grabbing multiple locks. Okay? And that says, essentially says, order all the data items in one global order. Okay? Always acquire locks regardless of the order in which they are actually accessed in your program. Always order them, acquire them in monotonically increasing order. Okay? So essentially that says, if you have two data items x and y, okay, and you ordered them 1 and 2, okay, if regardless of whether the transaction accesses x first or y first, if they're accessing both, you have to grab a lock on 1 before you grab a lock on 2. So if you acquire them in increasing order, you will not get a deadlock by definition, because both transactions will have to first get a lock on x, okay, regardless of the order. Is that clear what I said? Okay, so this basically, because deadlocks occur because there's a cycle. Okay, essentially 1 is holding x, and then 2 is holding y, and then you are basically waiting on the other. So you essentially get a this cycle. But if both of them try to acquire them in the same order, then you will never have this case where you have a higher level locked and you're waiting on a lower level lock. That is what has happened in this case. Okay, so you will essentially not have cycles by definition. Okay. That's just an example that I gave, so you can write deadlock-free code. Okay, if you have code that grabs lots of locks, if you logically order them in your mind and make your code get them in that order, you don't have to grab all the locks, but you have to always get them in increasing order. Then you will never get a deadlock where you hold a lock on a higher level data item and you're waiting for a lower level. Because by definition, you should have gotten that other lock first if you're acquiring them in order. Okay. So transactional system will have to use these kinds of rules if they want to avoid deadlock as well. By definition, two-phase locking doesn't require you to do that. Yes?
So this works for a simple query where you know x and y a priori, but for a complex query where suppose
recognize a data item that came out from that. You won't really have that knowledge beforehand, right?
So that's a good point. The point is, in simple queries, you might be able to do this, right? So you can actually go and analyze your query beforehand and figure out what it did. But if you're going to generate the new data and insert it into the database and grab logs on it, etc., then this may be harder to do. You're right. I'm not saying this is what you should do in databases. I was simply saying that when you are writing code, threaded code, this is a good way to avoid deadlock. Okay. Other questions here? Okay. So in the remaining few minutes, we are going to look at one last technique, which is timestamp based. This is also a way to essentially avoid problems with respect to conflicts and so on. Okay. This technique doesn't use logs, it uses timestamps. Okay. You could use logical clocks to do this, but let's assume that you don't need to use logic. If it's a single system, single database, you can use real clocks because there's nothing to synchronize. If you have distributed databases, you might either have to use logical timestamps or things of that sort. Okay. But for this example, let's assume that it's a single machine, we can just use real clocks. Okay. So the basic idea is whenever a transaction starts, you essentially timestamp it with its start time. That's your timestamp of that transaction. That's when it started. Okay. Whenever that transaction is going to access any data item, you are going to look at when was that data item read most recently and when what is written most recently. And then you are going to compare the timestamp of your transaction with the timestamp of the data item and decide if there is a conflict. If there is a conflict, you will abort. Okay. And the rules for conflicts I am going to just show you. So the basic idea is the transaction is going to abort if a newer transaction has already gone and modified some data it's trying to access. Okay. That's the rule we want. You start a transaction, some newer transaction has come and modified some data. Now you are trying to access that data. We don't allow that. You say you abort and then you should start later. That because that violates our sequential property. We want to assume that you are giving the serializability, so you don't. This is not going to give us that. Okay. So to implement this, the rules are very simple. For every entry in your database, you are going to maintain two timestamps. Okay. The most recently read time and the most recent write time. Okay. Which is the transaction that has read this data item? Okay. What's the transaction that has written to it? You just record the timestamps of those transactions for every item, and the transaction itself will get a timestamp. Okay. And these simple rules here are going to do it for us. So if you want to read X in the database, okay, you take the timestamp of the transaction that's trying to read X, you compare it with the write timestamp. Say if there is a newer transaction that has written to it, abort. Okay, that's what that says. If your timestamp is less than the write timestamp, max write timestamp, that means that a newer transaction is already written to that record. So that's not allowed, so you'll simply abort. Okay. Otherwise, you'll perform the read, and then you're going to essentially update the timestamp. Okay, the read timestamp in particular. Okay, to do a write, you're going to check the transaction timestamp and say, is there a newer transaction that has read it or that has written to it? Okay. This is going to be a read-write conflict. I'm trying to write, a newer transaction has already read it, and that's a write-write conflict. This is I'm trying to write, a newer transaction has written to. So you explicitly check for both of these cases. And if either of those occur, you are going to abort. If neither of those two occur, then you write, and then you update the write timestamp to this value. Okay, and then you're done. So you're actually looking at timestamp to reason about in what order have transactions accessed the data item. Is there a newer one that did something that I'm trying to do? If so, I should abort because that's not going to guarantee serializability. Okay. And so this is a timestamp based approach that is also going to give us concurrency control. Okay. You can have multiple transactions execute. You're explicitly checking for the presence of read-write and write-write conflicts. Is that clear? Okay. So we will stop here for today, and we are going to continue next time.